Hi, so we're finally going to get into some real life statistics in this video. And what I mean by real life statistics is we're going to take what we learned from the theoretical back end, which is where we've spent the last few chapters, and we're going to move back to the kind of things we talked about in chapter one, uh, which is collecting data from the real world. And remember that in real life, typically no one hands you right the defining information for some random variable. What you get instead is observations about how that random variable behaves, and from that you'd like to be able to say something intelligible about the random variable itself. So um, let's start with a fictional hypothetical situation. So, suppose uh, you weigh 35 purple micro elephants. Uh, so we weigh 35 purple micro elephants. Purple micro elephants are a made up animal, so I can, play with the numbers here to some extent. And let's suppose their average weight is, let's say, 125 pounds with standard deviation 20 pounds. How much, on average, do purple microelephants weigh? Alright, so you can imagine how this generalizes to an actual example, but let's say there's some type of animal and you get a bunch of them, so 35 in this case. In real life, that could be more, it could be less. Hopefully, it's more. And you weigh them, and when you weigh them, they're gonna have an average weight, right? So that is some sort of X bar, right? And you're gonna get they have a standard deviation of 120 pounds, so that's some sort of S, right? And this is the size of our sample N, and we want to know how much on average do purple microelephants weigh. So I weighed these 35, and from that, can I determine how much of all the purple microelephants in the world, what the average weight is? And the answer to this question, of course, uh, maybe it's not entirely obvious, but it's very important to realize that there's no way that we can actually answer this question, right? Unless these 35 purple microelephants are literally all of the purple microelephants in the world, there's no way that by taking some subset of those purple microelephants that you can somehow determine exactly how much all of them weigh. That's impossible, right? You don't know whether or not these 35 are slightly heavier on average than the average purple microelephant, or slightly less heavy, or that maybe the next microelephant you weigh weighs like 1,000 pounds. There's no way to know that, right? And so it's very important to say and to admit right up front that we don't know how much on average purple microelephant weighs. That being said, if instead of 35, let's say I weighed 3,500 purple microelephants, and the average weight was still 125 pounds, well, that wouldn't tell me that their average weight was 125 pounds, but I'm willing to feel comfortable that we're close, right? And so, um, the title of this video, as you can see, is Confidence Intervals. And so what we'll be doing in this video is figuring out, it's like, all right, um, finding intervals, right? So instead of a specific value that's going to say, all right, this is exactly what the average weight is, we're going to get a range of values. And then we're going to discuss how confident we are that that range contains the actual average weight. All right. So to see how we think of this, right, we imagine that out there somewhere maybe are all of the purple microelephants, right? And from that collection of purple microelephants, here's a sample, right? The sample. And then this sample has main 125, S20, right? And so there is also, of course, the purple microelephants say do have an average weight. And what is that average weight? We don't know what that average weight is. And it's also distributed with some standard deviation. And we have no idea what that is either, right? In order to find this information, you would have to gather up every single purple microelephant in the whole world and uh, throw them on scales, and presumably we can't do that. But, you know, most of the time biologists don't get to do that. I don't think anyone, for example, who works with like fish has weighed every fish on Earth, and that doesn't seem like a feasible thing. So there must be something we can do, right? So uh, this variable, say, is x, right? Let's just call this random variable x, which is the weight of a purple microelephant. I don't know what that is. And I don't know the shape of it either. I don't know what type of random variable it is. It could be normal, but it might not be as well, right? On the other hand, let's say the average value of 35 purple microelephants, well, that thing is likely to be normal, right? By the central limit theorem. The central limit theorem, because we've taken a sufficiently large sample of 35, implies that this the average of 35 microelephants should be a normal variable. And if we were to take an additional assumption, let me pick a color here, and say that our sigma was close to 20, or approximately 20, right? Then the sigma of my sample size of 35, that thing is going to be approximately 20 over the square root of 35, right? And so this expression here is what's called the standard error. And this is the how do I want to phrase this? This is the standard deviation of the sampling variable. Because you see what's going on is that the x35 here, it's also a random variable. It has a mean and it has a standard deviation, right? So if we assume that the sample standard deviation we originally measured was accurate, then once we take into account the fact that the sample has size n, the standard error is s over square root of n. And this 125, this is what we call the point estimate. Right. And so that's our current, this thing here is our current estimate for what the mean might be. Now, we're almost certainly wrong, right? There's almost no chance that I reach into this bag of all of the elephants in the world, pull out 35, and just dead on happen to get the exact mean. But let's see what happens, right? What we should know is that we should note that the mean of this random variable here is the same as the original mean, right? That's something else that we discussed in the central limit theorem video. And so that whatever the average weight of purple microelephants actually are, it's also the average weight of the averages of 35 purple microelephants. And so let's see some scenarios here. Let's play some scenarios out. It is possible, right, that maybe, like I said, the average weight of purple microelephants really is 125. And then our 125 just happens to be right there, right on top of it. It is possible that the average, excuse me. It is possible that the average weight, let's say it's a lot less than 125. Let's say it's 90, right? In which case, the chances of us getting a outcome or result like 125 is actually kind of small, right? It would be an extremo right right outlier type of event. And similarly, it is possible that our it's got to stop doing that. Maybe purple microelephants weigh a lot more than the mean that we got, and then the 125 that we got is a way leftward event. By the way, the only reason I'm able to draw a normal curve at all to represent the possible shape of these distributions is because of the central limit theorem, right? Because I've taken an n sufficiently large that I feel confident in saying, well, no matter what the actual distribution of the purple microelephant weights looks like, and no matter what the actual average weight really is, by sampling a large enough sample size, I feel confident that the average weight of 35 purple microelephants, that thing is normally distributed. And so I get to draw things with these shapes. All right, so when you put it all together then, what you get is an X bar, or a point estimate of 125. And then you get a actual population average that could be anything, right? But when we look at this picture here, right, it does seem as if it should be more likely, it's more likely we got a result of 125 if the actual mean is closer to 125. And if it's really far away from 125, then the chances of us getting a result like 125 is less. And so if I look at the possible distributions of where the mean could end up, it seems as if uh, we should be, the true mean is more likely to be closer to the 125 and less likely to be farther away. And so the distribution of where the mean could be, the actual true mean, is, you guessed it, a normally distributed curve with standard deviation equal to the standard error, which is our sample mean over the square root of n, which in our case is 20 over the square root of 35. All right. So, how accurate, in order to predict what the actual mean might be, it now depends on how confident you want to be in the answer. Well, you want to be 100% sure that you have an interval that contains the true mean, then you have to go between, well, negative infinity and positive infinity, basically, in order to get 100% confidence. And like I've mentioned before, there's no way that you can say with 100% confidence that the mean actually falls in any given finite length interval, because for all you know, all of the purple microelephants wrote say way more than that, or way less, and you just can't account for that. But if you only want it to be 90% accurate, say, you could go out far enough to get maybe 90% of the curve between these bars. If you want to be, say, 95% accurate, you could go out even further, right? And then you could say, well, that's 95%. And if we wanted to be even more accurate, we could go out even further than that and say, well, that over here, that's 99%, right? And so the confidence interval, a C% confidence interval, is something that's bound to the left by the mean minus the standard error times z, and bound by the right by x plus the standard error times z, where z is determined by c. And we call this term the margin of error. And the reason we call it the margin of error is because what we want to imagine is, all right, you have a point estimate x bar, right? Over here, say on the right, we have x bar plus SEZ, and over here on the left, we have x bar minus SEZ. And so these distances here are both size SEZ, right? So we start from the point estimator, which is the sample mean that we measure. We go out by the margin of error in both directions, and that's how wrong you could be on either side. And so let's clarify something, right? What do I mean by Z is determined by C%? Well, what I mean by that is, again, we have our x bar, x bar, and we have our curve, and well, that's if we have C%, if we want to get the C% interval, I want C% chance that we fall within this range. What are those Z values? And this is pretty much exactly, right, what we've been doing in chapter 3 when I say, all right, find the K values so that if I go plus and minus this K, I get blah percent within this range, right? Now, instead of a K, it's just a Z, and the margin of error, that's that K, all right? And so let's kind of back it up to the example that we've been working with here. So we know that our mean is 125 and our standard deviation is 20. Well, let's go ahead and recap those things maybe. Let's say so we measured an average weight of 125 with standard deviation 20, right? And for just for fun, let's go ahead and compute the standard error, which is 20 over square root of 35. All right, and let's say I want to compute a 90% confidence interval. And so if I compute a 90% confidence interval, right? What that would look like is, all right, I want to figure out what 90% is from the center, right? And that gives me a Z value of 1.6485. 1.64485. Then I could go ahead and say, well, on my right hand side, I get 125. That's my point estimator, right? Plus my standard error of 35 times the Z value, which I said was 0.64485, and that gives me a right bound of 130.56. Let's just go 2 places for now. All right. And if you remember the way we computed the confidence interval was plus the margin of error and minus the margin of error. So if I subtract the margin of error, that gives me 119.44. All right. So and it's very, very important for us to know what exactly this means. And so what this means precisely is I am 90% sure the average weight of purple microelephants is in the above interval. All right, so that means I'm 90% sure that between 119.44 pounds and 130.56 pounds, that in that range, that's where the actual average is. Okay, but what if I don't want to just be 90% sure? What if I want to be 95% sure? Well, 90% is here. If I want 95%, I have to go out more, right? I have to cast a wider net. So, uh, let's go back here and go from 90 to 95. But you know what? I don't feel like doing all of this arithmetic that I did over here again anymore. I mean, we could, uh, but wait, let me just go ahead and copy paste that so we can have the minus and the plus. So I have 119.44, 130.56, and let's go back here. Say, all right, I want to bump up to 95%. But you know what? Didn't I say that the distribution of the actual mean was going to be normal? And it is going to have mean 125, and the standard error was 25 over square root of 35? All right. Then that gives me on the left an x value of 118.37. And an x value on the right of 131.63. On the homework, you might want to round a bit more than this, but I'm just doing this for shorthand's sake. You can all see the decimal expansions go on for a little bit more. All right. And then my z value in this case, we can see is 1.959964. So if I go out here and I go 1. What did I say? 959964. Then I get 118.37, 131.63. Which is exactly the values we got here, right? And if I go back and look at what this means, it means that if I replace with 95%, then yeah, I'm 95% sure that the actual weight of purple microelephants falls within this new range. My right hand is a little bit bigger. My left hand is a little bit smaller, right? And that just means it took my thing, I bumped it up, and by bumping up some, I picked up another 5%. All right. Let's say I want to be 99% confident. So I need to go out now further, right, in both directions in order to get 99%. Then I bump that up to 99. And on the left, I get 116.29. And on the right, I get 133.71. And let's say my z-score, 2.5758293. 2.5758293. Copy, paste, 116.29, 133.71, right? Which is exactly what we said. Go back over here. Yep, my x value, my x value. Great. Right, and so we can see again that I bumped my values out even wider, right? From 119 for 90% to 118 something for 95 to 116.29 for 99. So these values get smaller, these values get larger, 130, 131.63, 133.71. So the more confident I want to be, then the wider I have to cast my net, right? And so I'm 99% sure that the average weight is going to be between 116.29 pounds and 133.71 pounds. All right. So, um, two sort of final concluding thoughts. One is that most of this stuff just seems like formula chasing, right? It just like there's an X bar, there's an SC that has a formula, you plug stuff in, and then there's a margin of error, which is a formula you plug stuff in, and then you add and minus and you get stuff. And formula chasing is the lowest form of math. It's really not where I want to focus to be on at all in this class. What I want us to be doing is thinking about what things mean. And so whenever there's any sort of formula chasing nonsense, we just go ahead and give that work to a machine. And so here we have a calculator for Z hypothesis testing, and one of the options here is confidence interval. So what we have here is sample size 35, a mean of, so sample mean of 125, sample standard deviation of 20. And the confidence level is going to be C is equal to 1 minus alpha. And let's not worry about what alpha means just yet. But if alpha is 0.1, then my confidence will be 90%. And so if I plug that in, I get the 119.44, 130.56. If I want 95%, oops. Then there I get my 114.37, 131.63. And if I want 99%, then my alpha needs to be 0.01. I get 116.29, 133.71. So we get those numbers right away. And we can see, right, we can watch this interval get wider as we need to capture more and more of the data, right? The wider out it goes, the bigger the percentages go. Sorry, I don't know if we actually saw the numbers earlier. 1, 05, 01. Right, and it tells you, right, the confidence level right here. Okay, so, and so let's go back to our question here. And so another thing that could come up is someone might ask, all right, well, let's stay here for a moment. We got this 99% confidence interval, And the range is between 116.29 to 133.71. So you have a margin of error about 8.71 pounds. And so what if someone looks at that and goes, no, I want you to be 99% confident and I only want you to have a 1 pound margin of error. So let's suppose someone tells you that they want 99% confidence, 1% margin of error. And you might imagine that this is fairly likely thing to happen, actually, right? Or sorry, not 1%, 1 pound, right? So you want to find the exact weight of microelephants within one plus or minus 1 pound. And so, sure, like you might be working for a company, you might be working as a researcher, and you gather up some data, and you say, all right, I'm 99% sure that the actual average of this thing we want to study is from here to here. And they say, no, that's way too wide, that's not usable, we need you to narrow that down. So let's back all the way up to this page here and go, all right, you go back to the drawing board and go, okay, what of these things is actually under my control that I could do differently as a person? Well, I can't control what the mean is or what mean I get. I measure, and then whatever mean I get is the mean I get, right? I definitely can't change S, right? Like, unless you go out and like genetically engineer your own elephants or slaughter any of the outliers that exist in the world, you don't get to control how variable uh, uh, a random variable is, and that might be considered unethical, right? And they've already told you they want 99%, so you don't even get to control uh, the z-score here, right? You don't even get to control this. So all of the things that go into constructing a random variable, or sorry, confidence interval, of all the things that go into that, the only thing under your control is n, right? You can go out and get a bigger sample. You can conduct a new experiment and get more data. And so if you need to make your results more confident, then you can go out and change the number of elephants that you measure. And notice this, as n goes up, square root of n gets bigger. As square root of n gets bigger, this fraction gets smaller. So the standard error gets smaller. As the standard error gets smaller, the margin of error gets smaller, right? So if you want a smaller margin of error, you need a bigger sample. And this is perfectly in line with common sense, right? If you want to be more confident in your results, if you want to be more accurate, then you need to measure more things. You can't just measure 2 elephants and call it good, right? And so presumably you don't want to just trial and error, keep taking bigger and bigger samples until you get a 1 pound margin of error. Presumably, we would like to know this right away, right? So, 99% confidence, 1 pound margin of error. Well, what do I know? How big? So, the question I'm asking myself here is, how big should n be? Right? Like, how many elephants should I go out and measure? And I want to know this before I go out and conduct this experiment, because again, I don't want to keep doing this over and over again. I just want to know right off the bat. All right. Well, what do I know? The margin of error is equal to your z-score times your standard error, which is your s over root n. Right? And what that means is that the margin of error times root n is equal to z times s. And that means root n is equal to z times s over the margin of error, which means that n is equal to z squared times s squared over the margin of error squared. All right. And so in our specific case, my n is equal to, well, the z squared, what's z again? Well, that's, did I minimize that window? All right. For a 99% confidence interval with the z value, let's, for the sake of having space on our screen, let's just say it's 2.576. Squared times my s, which is 20, squared, all over the margin of error that I want to have, 1 squared, right? And so I could go ahead, I need to bring that back, excuse me, and yeah, let me just boot up a new blank graph. 2.576 squared times 20 squared, and this is redundant, but let's divide all by 1, which doesn't change anything. 2.65.3, which of course is not a realistic answer because I'm not going to go out and measure 0.3104 of an elephant, right? So the actual n I would use is 2,655 elephants. Right. And I need at least 264.3 whatever. That's not actually possible, but 2,655 elephants is possible, right? And let's just kind of go into detail on this expression that I wrote, that n is equal to z squared s squared over margin of error squared. Let's just see if this is like, I mean, we got it from algebra, so it's true, but does it make sense intuitively? Well, the more confident you want to be, right, the bigger your C for confidence level, the bigger the Z value of the interval they have to go out and grab, the bigger the Z value, then the Z squared gets bigger, and that makes n bigger. So, right, the more confident you want to be, the more data you need to get. Makes perfect sense, right? S squared over here. Well, if microelephants don't vary a lot in weight, then we don't need to get that many to get a good sense of how much they weigh on average. If, on the other hand, they're way all over the place, and some weigh 3 pounds and some weigh 100 pounds or something, you're going to need a lot of microelephants to really get a handle of what the average weight might even be. And so, the bigger the variability, the more of these guys you need to weigh. So, bigger S gets, bigger N gets. And margin of error, well, if the proposed margin of error is wide, and it can be within like 10 pounds, we don't care that much, then you don't need that many data points, right, to be that accurate. On the other hand, if you really want a tight margin of error, it's like I want to know within a millionth of a pound what the average weight is going to be. Well, you're going to need to weigh a lot of elephants to make that happen, right? And so the bigger the margin of error can be, the less you have to worry about how many you need to measure. And the smaller the margin of error is, the more accurate these results need to be than the bigger n needs to be. All right, so hopefully that was helpful. And in the next video, we will discuss the philosophy behind hypothesis testing.